Hello everyone, welcome to JG Chemistry. Guys, this is our first video on organometallic compounds. This topic is very important for CSIR NET examination, GATE and M.Sc chemistry students. In this video, we will learn about heptacity and effective atomic number, or we also call it 18 electron rule, which is very important and the very first topic in organometallic compounds to study. So whenever we start organometallic compounds, first thing which we study is 18 electron rule. And to study 18 electron rule, to calculate it, we should know heptacity. So let's begin. We'll see organometallic compounds. What is organometallic compound? As the name suggests, organo plus metallic means you have a complex which is made up of the organic part as well as you have the inorganic metal. So you have basically the organo and metallic bond, covalent bond formation between the organometallic compound. So you have metal and the organic part here. Basically, metals are electropositive. So here the metal will bear a positive charge and the organic part will bear a negative charge. So in this way, the organic part will act as a nucleophile. So you should know that here the organic part will always behave either as a nucleophile or as a base, and the complex can exist in various oxidation states. So that we will see while discussing and calculating the EAN. Now, what about the stability of the complex? We will see that normally we have the transition metals which exist in different oxidation states and has sp-d orbitals here. So we know that s orbital occupies 2 electrons maximum, p occupies 6 electrons and d occupies total 10 electrons. So if we count, total number of electrons are here 18 electrons, which means it attains a noble gas configuration, and so we say that the following complex is stable complex. So basically in this way we says 18 electron rule which governs the stability of the complex. So this was the overview of organometallic compounds. Now we will discuss about EAN, that is effective atomic number, or 18 electron rule. So what is 18 electron rule? Basically it is the sum of the electrons on the metal and plus the electrons which is donated by the ligands. Now these are the steps which we have to follow while calculation of the EAN or 18 electron rule. That first step is we should know how many numbers of electrons are there on the metal in the outermost shell. Second is the electrons which are donated by the ligand to the metal, and is there any charge on the complex, like either positive or negative charge. If you have positive charge means you have to add -1. If you have negative charge on the complex, that means you have to add +1. Why it is so? Because positive charge means it has lost 1 electron, so you have to subtract it. Negative charge means it has gained 1 electron, so you have to add 1 electron. So depending on the charge, how many charge is there, +2, -2, accordingly you have to add or subtract. So we'll see first is how to find out the number of electrons on the metal. So these are the transition metals which we have written, having the electrons contribution 4 electron group, 5 electron, 6, 7, 8, 9 and 10 electron group. So in this group 4 electron you have titanium, zirconium, hafnium. For 5 electrons you have vanadium, niobium, tantalum, and so you can see 8 electron contribution iron, ruthenium, osmium. For 10 electron contribution you have nickel, platinum, platinum. So basically to calculate the EAN you should learn this table where you should know the following group the metal has 4 electrons, let's say in this case titanium, zirconium, hafnium, or if the metal belongs to the group where you have iron, ruthenium, osmium, it belongs to the 8 electron group. So the outermost shell has for this particular group of metals 8 electrons. So if you follow the electronic configuration you will see. So this is in short a table. You can make your own tricks to learn it, but you have to learn this table. And in this one exception, normally we say that the complex which has 18 electron rule are most stable. But if you see here, the smallest size 4 electron and largest size 10 electron are the exception here that follow and makes the complex stable in 16 electron itself. That is because of their size, overcrowding and repulsion occurs, and it makes it stable in 16 electron configuration. So learn this table to find out the number of electrons for the metal. Then the second step was the electron donated by the ligand. So now there are two categories of ligand which we have. One is non-hydrocarbon ligand, other is hydrocarbon ligands. For non-hydrocarbon ligands, you have this list which you have to learn, like you have halogen, hydrogen, nitroso and CN group, which if you have as a ligand contribute 1 electron to the metal. If you have PO3, CO, carbonyl and POR whole thrice, which belongs to the ammonia nitrogen group, nitrogen phosphorus, as it forms 3 bond molecule and it has 2 lone pairs. So basically it contributes 2 electrons. So you can see the other is also in the list, and you can notice here NO you have in both category. One is it is donating 1 electron, in other case it may donate the 3 electron. Why it is so? You can see the shape of NO here. It is either linear. If it is linear, it is contributing 1 electron. If the shape of the NO is bent or triangular, then you can see the pi bond electrons are also contributing along with the lone pair. So total 3 electrons donated to the metal. So that we will see while solving the problem whether it is contributing 1 or 3. So you have to learn the number of electrons donated by respective ligand. Hydrocarbon ligands, where we have heptacity term. As I told you, you should know heptacity to find out the EAN. We will start with the very first simple ligand Cr3, where 1 carbon is attached to the metal, means here 1 carbon is donating its electron. Each carbon donates 1 electron. So basically here this alkyl group will donate 1 electron to the metal, and so the heptacity will be indicated by eta 1. Now alkene, you have alkene pi bond here, and you can notice the metal is bonded to the center, means 2 pi electrons are contributing and donating to the metal, and so 2 electrons are donated. Its respective heptacity is eta 2. For allyl radical, allyl is the 3 carbon is present with the 1 double bond and a free radical. So it is in resonance. We can represent like this, and you can notice here the metal is from the center, it is bonded, means all the 3 electrons are donating to the metal. And so the number of electrons are donated 3, eta 3 is its heptacity. For conjugate diene, you can notice here you have 2 pi bonds and the metal is bonded to this conjugated diene from the center, means all the 4 pi electrons are contributing and donating its electron to the metal. Because of conjugation, resonance is present. 4 electrons are there, so eta 4 is its heptacity. Next you have dienyl radical, cyclopentadienyl radical. You can say here 5 carbon is there, the free radical is in resonance, and if the metal is bonded from the center, means all the 5 electrons are donated to the metal, so the heptacity is eta 5. Similarly for trienes or arenes, benzene, the metal is bonded from the center, means all the 6 electrons are donated to the metal, heptacity is eta 6. Trienal radicals, it may be cycloheptatrienal radical, total 7 electrons are there and the metal is attached to it from the center, means all 7 electrons are donated to the metal, eta 7 is its respective heptacity. Tetraenes means you have 8 electrons and the metal is bonded from the center, means all the 8 pi electrons are donated to the metal and its respective heptacity is eta 8. And so you can find out the heptacity and the number of electrons donated to the metal. Third step is, if any positive or negative charge is present on the complex, accordingly you have to subtract or add. Now we have to note here Let's say you have a conjugated diene system, but instead of from the center the metal is bonded only one of the double bond. That means the total contribution of the electron is 2 here. So the heptacity will be eta 2. It's not eta 4 here because the other pi bond is not giving its electron. Similarly, you have allyl radical, but only the pi bond is giving its electron to the metal. So the contribution is 2 electron. Eta 2 will be its heptacity. You have arranged systems like you have 6 pi electron here, but the metal is attached only with the one double bond, not from the center. So the contribution of the electron is only 2 here. So heptacity is eta 2. So you have to be careful while seeing whether the one double bond, 4 pi electrons or all the 6 electrons are giving to the metal, that you have to be careful. In this you can see you have again benzene, but only 4 pi electrons are donated to the metal. It is between the 4 pi electron, not on the double bond. So 4 electron means heptacity is eta 4. Now here you can notice the difference you can make out from 2 electron to 4 to 6. From the center means all the 6 pi electrons are donated, and so the heptacity is eta 6. And the fourth one is if the metal is bonded from one carbon only of this arranged system, that means the contribution is only 1 electron, and so the heptacity will be eta 1. So don't get confused. You have to be careful while just seeing the hydrocarbon ligands, how many electrons are donated. Now we'll solve the problems. You have iron here as a metal, and you should know how many total electrons are contributed. You should know that iron contributes 8 electrons, and you have 2 cyclopentadienyl rings, 1 Cp. 1 Cp is 5 electrons. The metal is bonded from the center, means you have total 10 electrons which are donating its electron to the metal. 5 into 2, so total 18 electrons. If you sum it, 18 electrons means the complex is a stable complex. And so they ask you, they will give you this structure and ask you to calculate the effective atomic number for this, or whether it is stable or unstable. Does it follow the 18 electron like that? You can show. Now in this you have molybdenum, you have 1 Cp, cyclopentadienyl, contributing 5 electron, means its heptacity is eta 5. You have one allyl system, again all the 3 electrons are donating its electron, means heptacity is eta 3. You have 1 nitroso and 1 carbonyl group. 1 carbonyl we know it donates 2 electron. NO we have to find out whether it is 1 or 3 to make it stable. Molybdenum contributes 6 electron. CO we have seen, NO it may be 1 or 3, Cp 5, allyl 3, and you have 1 positive charge, means you have to subtract 1. Plus positive charge means you have to subtract 1 because it lost 1 electron, 1 positive charge. So if you calculate with respect to, let's say, NO 1 electron, then you get the 16 electron. But if you take 3 electrons, then you get 18 electrons here. So basically here 18 electron complex makes it more stable than the 16 electrons. So here the NO will contribute to the 3 electrons, and the shape of the NO will be bent or triangular. Next molecule you have chromium complex, where chromium contribute to the 6 electron. It has with the same molybdenum group. Carbonyls are 6, 1 carbonyl contribute 2, 6 into 2, 12, and makes it 18 electron, makes it more stable because it attains a noble gas configuration. You have again chromium complex, 6 electron, 1 Cp. If they don't give the structure here, Cp, then take it 5, and carbonyl, you can see 3 carbonyls are present, so 6 electron, because ultimately we have to see whether it makes attains a noble gas configuration or not. But here you can notice it is 17 electron, which makes it unstable. So something we have to do here on the complex to attain the noble gas configuration. So what we have to do here, we have to incorporate a charge, and the charge should be minus, because if you have minus charge then you have to add 1. Minus means it is gaining one electron, and after doing that you have to add plus 1 means it attains the noble gas configuration 18 electron and makes it stable. So basically this complex becomes more stable when you incorporate a negative charge, because it attains a 18 electron configuration. So like that also a question may come for you where you have to stabilize the complex by putting one charge either positive or negative. Next problem, you have a rhodium complex, you have PPH2, 2 PPH2 is there, 1 phosphorus, it's like same like nitrogen, only phosphorus is bonded to rhodium, means 2 electron from each phosphorus, total 4 electron. Cp is contributing from the center, 5 electron, and chlorine 1. Rhodium belongs to the 9th group, and the outermost shell electrons are 9 electrons. As I told you, you have to learn that by making some tricks, or you have to practice by writing it, and so you can solve this problem easily. Cp, chlorine, 2 PPH2, total 4 electrons because each contribute 2, and you have a 1 positive charge means you have to subtract 1. It brings 18 electron configuration means it is stable. Another one where you have ruthenium complex with positive 2 charge and 2 aromatic ring. You can notice here aromatic ring is bonded to the metal from the center, so means all the 6 electrons are contributing here. Ruthenium belongs to the 8 electron group, outermost is 8 electron, 2 pH, 12 electrons. So if you calculate it, it is coming 20 electrons, which is unstable. So we have to do something to bring 18 electron, means we have to subtract 2. And how we can subtract 2? By putting 2 positive charge, which means it is positive charge means it is losing 2 electrons. So minus 2 and makes it stable. Now this is a titanium complex where we have seen that it is exception that makes 16 electron complex stable because of its small size. So titanium 4 electron series Cp, you can see here Cp is total 2 Cp are there, 10 electron, each chlorine 1 contribution, so it is 16 electron which makes it stable. Titanium complex. For iron we have to check 1 Cp 5 electron, 1 alkene 2 electron, carbonyl 2 electron, total 2 carbonyl are there, so 4 electrons, and you have 1 positive charge, so minus 1. Iron belongs to the 8 electron outermost shell configuration, so it brings 18 electron configuration. Now finally this example belongs to the 10 electron platinum series, which is, you can say, because of the large size we have seen that it makes a complex stable in 16 electron also. So we'll see here pH is giving only instead of the ring. We'll see how many electrons are contributing. If it is showing like that, usually we indicate 1 electron. So we'll see platinum is 10 electron, each chlorine 1 electron, total 2 is 2 electron, each cyanide group is 1 electron, so 2 electron, 14 electrons, and now you have 2 pH, each is contributing 1 electron, so 2 electron, 16 electron configuration it is giving, which is a stable configuration for the large group metals because of the overcrowding. So you can see here the effective atomic number calculations along with the heptacity. I hope you understood how to calculate it, and you will solve all the related problems comes to you either your NET examination gate or M.Sc chemistry examinations. Happy learning.